Hello, ladies and gentlemen. Thank you for joining us in this presentation this afternoon. We will discuss quality consideration in wireless networking. I am Michel from company MTI Wireless Edge, and we will discuss some of the wireless aspects. Now, this presentation will be different from what we have been going through all those 2 days, because you probably have dealt mainly with switching and routing, and I will be discussing aspects for wireless communications. In a typical network, of course, we have the famous IP cloud, we have servers, and then you have your customers. Now, in principle, the connection between the users are the same via the cloud. However, there are some fixed lines like fiber or copper, and there is RF links, wireless communications, and I will be focusing more in this area, and we see that in real life, the RF link does not behave the same as your fixed line like copper or fiber. Basically, you are very familiar with this arena, your backbone where you connect to MikroTik or other switches. I will be discussing the red area, which means point-to-point, point-to-multipoint, and general broadband wireless access. Now, there is a general conception of many people who think there is no big deal to do wireless communication. You don't have to draw fibers or copper, so what's the big deal? The thing is that there is a few topics to be considered when going wireless. The question I'm asked very often, and that's the first question, is how much does it cost? MTI, we are an antenna manufacturer, and the first question is, how much does it cost? What I'm saying is, it's a relevant question, and we get to that in every discussion, but at the end and not in the start. Meaning, it should be not the first question and certainly not the only question, but in the end, you should consider what do you get for your money. Now, when you talk about the wireless network, you should look at the broad picture, meaning what kind of network are you building, who are the customers, what are their requirements, what applications are you running over your network, what is the throughput you need, what are the distances that you have to cover. And as we'll see, the antenna in a wireless network is the most critical part, because the antenna you choose will directly influence the distance of transmission you're able to cover, the throughput which you will be able to achieve in the different applications, quality of service, and also very importantly, interference. Usually you don't have just one antenna, it's a crowded environment, you have interference. If you're building a network, you have to reuse your frequencies, reliability and survivability of your network. All those topics must be considered, and some of the antenna parameters which influence what we've discussed before are the frequency, gain, half power beamwidth, front to back ratio, side lobes, nulls, and so on. I will discuss some of those parameters for those who are less versed in wireless. This may be interesting to take note of a few parameters of antennas which are important when you choose your antenna vendor. Obviously, the frequency you're using, the question is whether you're using 2.4, 3.5, 5.8, and so on. 2.4 usually already is crowded, and so on. We have a very broad selection of antennas in all spectrum, so the choice is yours. It also depends whether you need licensing or not. The other point is gain. Gain is the energy in the direction you want, and you want to have maximum gain, But you have to consider, first of all, gain. You have to distinguish between the azimuth and elevation. Azimuth is the opening angle, and elevation is the up-down angle of an antenna. Now, what you see here is two examples with a mask, which is called ETSI mask, meaning a good antenna must be compliant to European standards. The European standard also fit maximum levels so that you don't push out a lot of power and destroy all the other communications. So we take great care to offer you maximum power, but within the limit of ETSI limitations, both in azimuth and in elevation. Now, another point to consider is main lobe and side lobe. Main lobe is the direction of communication you want. However, in antennas, you also have side lobes, which you want to have as low as possible, because side lobes, when you're sending in this direction, side lobes go somewhere to the side and may interfere with other antennas or other operators you may have on the same mast. And we'll discuss this later on. Now, another important point is beam width, meaning which opening angle does your antenna have. Now, the beam width is defined as minus 3D point, which means that this is this point here and here, which is half the power of the maximum power you have on your antenna. This is per definition the beam width. Now, we will see later on that some people are a little bit more liberal in the way they interpreted the beam width. I mentioned before the main lobe, and you can see here the main lobe. This is the direction of energy you want. If you're the base station and your customer is over there, you want to transmit maximum energy toward your customer. But in the antenna, also, you have some energy going backwards, and you want to have the ratio of front to back as low as possible, because energy transmitted backwards may again interfere with some other antenna installations. The main lobe is the central lobe. This is the energy you want. However, due to physics in the antennas, you also have some energy being dissipated to sides. Now, you want to have the side lobes to have as low as possible, meaning you want high side lobe suppression. Now, in some antennas, actually, we have seen that communication, if it was not set up correctly, some customer used side lobes for communication instead of the main lobe. You want to have those as low as possible because they create interference. There is another point to mention. If I talked before about the lobes, main lobe, side lobe 1, side lobe 2, side lobe 3, etc. In between the main lobe and side lobes, we have what is called nulls. The nulls is where you have no or very low energy. Now, the next point is, so far I was talking mainly about a single polarization antenna, but there is also the issue of cross-polarization, which means that a multi-polarization antenna may interfere with itself if you don't have good isolation. However, the term cross-polarization just means that the energy is perpendicular at the right angle. And often this term is used not correctly and is confused with dual polarization and dual slant. I'll cover this in a moment. You have a single polarization antenna, the most simple antenna, which transmits one energy level, usually in the vertical plane, and propagates through space. Now, often you want to transmit more information, you need more than one antenna. Today there exists technology which allows you to integrate more than one antenna into one physical space. So for example, we can use the vertical plane and the horizontal plane, meaning in one antenna, basically we have what we've seen before, a vertical antenna and a horizontal antenna. They are sending at 90 degrees difference. So we speak about dual polarization, vertical and horizontal antennas in one package. A similar approach is when I take my dual polarization antenna and I switch it by 45 degrees. Basically, I take this antenna, switch it 45 degrees, so the vertical and horizontal basically become plus 45 or minus 45. In principle, that's the same antenna. However, when we talk about plus minus 45, we are talking about dual slant antennas. Now you can get a dual slant application either by taking a dual polarization antenna and switching it by 45 degrees, or of course you can design from the start a dual slant antenna which has internally a different construction than the dual polarization antenna. Now, when we're talking about dual polarization antenna, for example, we can see here one antenna which is working at 5 gigahertz, 16 dBi, dual polarization. Now here you can see the antenna pattern of one antenna. Let's call it the blue antenna. We can see another antenna, which is the red antenna, and it has the same name, 5 gigahertz, 16 dBi, dual polarization. However, when we look at the two antennas together, we can see that this is not the same antenna, because look at the blue lines. Yes, in the center, they're pretty close to the value given, 16 dBi. But if you look at the lower area at 4.9, you see it degrades significantly to 12 or 11 dBi. Same for the high frequency, again to 10 or 11 dBi. However, the red antenna is more equal about the whole frequency. And of course, the result of this is that with a red antenna, which is a high quality antenna, you will get much more throughput. You can push more traffic through your antenna to your customer. So of course, you would prefer an antenna which is more even among the whole spectrum and not degrading in the lower limit or in the higher limit. Now, what you probably did not pay attention to is this area here, which means a single PCB and FR4. Now I'm discussing a little bit internal construction, meaning a dual polarization antenna can be manufactured in at least 4 different ways. I can build a dual polarization antenna by using one single PCB of a certain material called FR4, or I can build this antenna using 2 PCBs of FR4, or I can use 2 PCBs, FR4 and other material. I can use 2 different PCBs with different material. Now, why would I use 4 different ways to construct an antenna? The answer is because each antenna will have a different performance and will have a different cost. Because, for example, there is materials in which the raw material costs 10 times as much as the standard PCB. However, you get better performance. So in this example, you can see 4 different ways. Each of the antennas will be called 5 gigahertz dual polarization antenna, but will have different performance, will have different costs, because not just the engineering is different, in some cases even the material is different. So when somebody walks up to me and asks, how much does a dual polarization antenna cost? I have the answers for all 4 of them. The question is, what do you need? You want the most economical way, or you want the highest performance? So there is always a trade-off between performance and cost. So there's no simple answer even to a simple question, how much does a dual polarization antenna cost? It's like if I ask you, how much does a car cost? You're going for a Fiat or a Lamborghini? So in a similar way for the antennas. Now, another point which is interesting is, of course, specifications. Now, typically, antennas are specified over a certain range. In this example, from 5.1 to 5.9, that's the yellow area. You can see the red line, which is the specification. You can see that in our case, the antenna within the specification always performs better than the specification. The red line is the specification, the blue line is the actual performance. So as long as you're working within the specification, the gain actually is better than we write in the specification. However, if some customer comes to me and says, very nice, but I would like to use your antenna not at 5.3 or 5.7 gigahertz, I would like to use it at 5 or at 4.9 or at 6.1, then he still may use it. You may see some degradation in performance, but it does not fall off completely. So often, if you have some unique requirement which is close to what you need, you can use a standard antenna, and we don't have to develop a special antenna which has a broadband application, but you have to take care of the performance, whether, for example, in this example, 16 or 15 dB is still good enough. If not, you probably will choose a different antenna than what is now specified. I talked about gain, and in a very similar way, you have to consider not just the gain, but also VSWR, that is the energy which is returned to your radio. How much does it change? In this case, for example, we had a customer who asked to use this antenna in a broadband application, and it was possible because neither the gain nor VSWR did deteriorate very significantly. Another issue to consider, of course, is not just RF requirements, but environmental requirements. For example, whether your antenna is dust and waterproof. So usually you should look for antenna which is at least specified IP67, which means that your antenna is dust and waterproof. So when it rains, no water will penetrate, or when it's hot, no air will be drawn in, and so on. So this is one of the issues which is not often discussed, because people ask about frequency gain and not about environmental requirements. Another point, for example, is salt spray testing, meaning if you have installations near the sea, on an island, or even on ships, you need to make sure that the salty air or salt water will not harm your antenna. Therefore, a good antenna always will also specify salt spray testing, meaning you put the antenna in a salt spray chamber for 500 hours and you check the results, and so on and so forth. There is some other issues to consider. For example, solar radiation, when you put it up and it's in the sun 24/7 for the whole year and so on, that in time the plastic will not break and so on. So you cannot just use standard plastic. You need components and materials which can withstand sun radiation and so on. Another point, of course, is not just during development that you consider those points, but also in manufacturing, that you perform testing on the lots that you get from your vendor. Now, a point which is neglected by some Far Eastern or other vendors is actually quality standards. For example, antenna in Europe always should comply with ETSI standards, which is defines how much power you may use, etc., and some other standards like ROHS compliance and ISO certification. So you should make sure, in order to get the quality product, that your vendor adheres to all those standards. Now, I talk about vendor, it's not just the product itself. You want to make sure that the guy you're buying your antenna from is a well-established company, is in business for a long time, whether it's a private company or a public company. For a public company, you're able to check the listing of the stock exchange and so on. You can know what is their turnover, are they profitable, are they losing money, and so on. Of course, what are the technical capabilities, because you will be surprised how many antenna vendors manufacture antennas but are not even able to test them in-house. So once a quarter they go to some university and do some testing. A good antenna vendor has all testing capabilities in-house and performs not just during development testing, but also for each lot of production, checks and verifies the performance. Here you can see, for example, not just antenna ranges in-house, but also anechoing chamber in a high-quality vendor environment. And then, of course, another point which is not always considered well is the reliability of technical information. What I'm referring to is all vendors put out data sheets in which they describe their product and the performance of the product. However, some vendors, let's say, are quite liberal in the way they present their products, and they on paper show good performance. However, when you take the actual product and mount it, you can see that not always what is written in the data sheet actually is performed by the product. A high quality vendor will always use data sheets which actually reflect the actual product. Now, I will now come to a few examples from real life. Some of our customers has experienced, just to illustrate the points I made so far and how it may influence your network, because the antenna does not stand by itself. Here we have an example of an antenna which one of our customers had in his network. The antenna was specified as 29 dBi. The customer came to us and said, listen, I have a problem, I don't get the performance I expected. We checked the antenna, and as it turned out, the antenna was significantly lower in specifications. For example, at 5.47 gigahertz, the performance was even less than 25 dBi. So you have a deficit of more than 4 dBi. The antenna, I remind you, was specified as 29 dBi. So this was for the azimuth. In a similar way, you can see for the elevation, again, you have over 3 dBi deficit. So if this antenna is sold to you as a 29 dBi antenna, when in fact what you're getting is a 26 dBi antenna, the question is whether you still bought a cheap 29 dBi antenna, where in fact you got a 26 dBi antenna. In other words, you must make sure what you get for your money. So it's not just how much does it cost, but also what is the performance and how well does the claimed performance withstand testing or the actual product. Another example is some antenna which again was measured as a claimed gain of 39. Again, we can see here the discrepancy between low quality antenna and the high quality antenna. You can see the difference of a low quality antenna and high quality antenna, and the extra gain you get, which is at least half a dBi or more, both for the vertical port and the horizontal port. So what I want to say is, don't look just at the data sheet, but check what you get in reality. The same goes, I mentioned before, side lobes. So side lobe suppression is very important. So for a good antenna, you have more than 20 dB suppression for side lobes, and a similar way, if you have more than one antenna in one package, you need to get information on port isolation. Here again, you can see significant difference between a high quality and low quality antenna in the port isolation and side lobes. Now, this is not just paperwork. If you look at how this will influence your network, you will see that even a relatively small difference of just 1 to 2 dBi gain per antenna on the link already will translate to a gap of 2 to 4 dBi. And this already starts to be quite significant. Now, what I discussed before, side lobe suppression on port isolation will also, of course, influence the performance of your network. Because if you have high side lobe and poor port isolation, it will influence the quality of service, it will influence the throughput you're able to get from your system, and especially in today's adaptive systems, if the communication is poor, so your radio has to switch down, for example, from QAM 256 to QAM 64, which means that the throughput of your system will degrade by a factor of 4. This is not 2 or 3%. This is an order of magnitude which you will be able to have less throughput. So if you want on a system like this, for example, use it for video transmission, you will be in trouble. Another example is something quite unique. We have seen, again, a specification. I enlarge it a little bit, just for your convenience, of a base station antenna, which is defined as 100 degrees, 120 degrees, sorry. However, there is here something peculiar in brackets, which nobody actually pays attention to. So this is defined by the vendor as a 120-degree antenna, and he writes something like 6 dB here. But I remind you the definition of the beam width, not by us or any other vendor, but per definition is -3 dB. That's the value where half the power is transmitted, and this is per standard the beam width. Now, if this vendor writes something like this, we look at the graph which he supplies, and if I look at -6 dB, yes, it may be 120 degrees. But when I look at the defined stage, you will see that with a lot of goodwill, maybe it's a 90-degree antenna. Now, this is, of course, important not just for specification, because what you get actually is a 90-degree antenna. You were sold a 120-degree base station antenna. You rely on this, when in fact it's a 90-degree antenna. And it's not just specifications. If you now set up your system with 3 antennas, you think you have 3 antennas of 120 degrees. As a matter of fact, you have 3 antennas of 90 degrees. The result of this is that in between the sectors, you get very low or no reception at all. So if you have customers in this area, they will not be happy. So clients which are between the sectors will not get a signal at all or just a poor signal. What it means to your customer, or if you're a WISP or an operator, it means that you lose 25% of the coverage, you lose 25% of your customers, and you lose 25% of your revenues. So yes, you bought a cheap antenna, but you lose customers, you lose revenues, and so on. So bear that in mind when you choose the antenna, especially for base station antennas. Another example is the throughput I discussed. Now here I use numbers a few years back, so the absolute numbers are not too impressive by today's standards, but the relation still holds. A customer which was using high quality antennas got throughput of 80 megabit per second. Then he decided, well, I can find some cheaper antennas on the market. Let's replace the antenna I'm purchasing now with a cheap antenna. The result was that this customer just replaced the antenna and the throughput went down from over 80 megabit per second to less than 50 megabit per second, meaning you lose more than 40% of performance. Okay, you buy a cheap antenna, but excuse my French, you screw up the whole system performance. You invest in radio design, in engineering, in materials, and then you want to save $2 on the antenna, and you degrade the whole performance of your system. Now I remind you again, the absolute numbers, like 80 and 50 megabit per second, today is not too impressive, but today it's maybe even more important because now we're talking about MIMO antennas and so on, so we have more than one antenna in the package. So the penalty you would get if you choose a low quality antenna may be even more than 40%. Now, another issue is there is also some special antenna technologies. For example, I discussed the main lobes and side lobe issue, and in between we have the nulls as discussed before. So there is a special technology which is called null fill technology. This technology basically evens out. If you compare this antenna graph with this one, you can see that here we can see the nulls in between. In this antenna, the nulls are even out to a great extent. So this is a special technology which we call null fill, and here you don't get this low energy. The result of that is that if you look at the coverage of the antenna, you have the main lobe, then you have side lobe 1, side lobe 2. In between you have null 1, null 2, and so on. However, if I use a null fill antenna, the transmission over the whole area is much more equal. And you can see again here that it does not degrade so much as in this example. Now, here we have an example of an antenna, of a standard antenna and a null fill antenna. The red area is the area which is not well covered. This is a simulation of a standard antenna. This is the simulation of a null fill antenna. You can see that here the coverage without null fill is maybe something like 85% of the area. If you use the null fill antenna, the coverage of the area has been improved from something like 85 to 97 or so. So customers which were in this area now are being covered. And here you have a real life example of exactly this situation. Here you can see one of the vendors use a standard antenna. You can see in between the sectors very poor performance. And on the other hand, switching to a null fill antenna, much improved performance. Mind you, this is the same radio, same topology, same geography, same everything. So yes, a null fill antenna is more expensive, actually significantly more expensive than a standard antenna. However, if you look at the implications here, they are very severe, meaning here the reception is much improved over the whole area. The result of this is that you get improved coverage, improved throughput, and higher capacity for your base station. So what this translates to is that yes, the antenna costs more, but you can now give better service to your customer. You can cover more customers. You can put more customers on one base station. You can expand the cells, which means that you need less base stations. So the return on investment, even though the antenna itself may be more expensive, is measured in a matter of weeks. So the question is, well, for money, or what do you get for what you pay? So it's not enough to ask how much does it cost. The question is, what do you get, and what is the benefit you get if you choose to offer your customers high quality service. Now, for those of you who speak German, there is a German proverb which says, Papier ist geduldig, meaning you can put anything on paper. And this goes, we have seen some examples in the specification. You should check what is written in the specification, if that is what you get, or whether sometimes the specifications are overly optimistic, and when you install it, it doesn't work. I just here, yesterday had a customer who explained to me, yes, I chose an antenna vendor which on paper had much better performance than your antenna. I installed it, nothing worked. I chose your antenna, which was specified lower, but the performance was satisfactory and was very well. So bear in mind that you have to check this out. Another issue just is it pays if you choose quality, because in the long term, choosing quality components allows you to offer high quality service to your customers. Now, how much does it cost? I remember still the first question. It's a valid question, and we always are getting back. What I'm saying is this question should be answered at the end, because you have to consider what performance you need, which quality you need. Sometimes, yes, a simple antenna, if you have just one traffic from here over there, let's call it good enough antenna, will work fine. But if you have to build up a complete network with many customers, you have to consider interference. If you want to carry video over your network, what is the throughput you're able to carry? And then a good antenna makes all the difference in the world. So in a similar way that, yes, you can get from A to B with a bicycle, but if it rains, you want to take your girlfriend or your wife along and the suitcase, probably you choose a car and not a bicycle. Similar for antennas. It depends on the requirements you or your customers have. Now, another point is that you should consider for your MikroTik-based networks, what is the spread of the products your vendor has. For example, which frequency bands does he cover? All the frequency bands, yes or no? Which type of antennas, like base stations, CP antennas, omnidirectional antennas, is able to offer you, so you can work with one antenna vendor you trust. And of course, if you have additional questions, you're welcome to pay a visit to my stand in the other room and to discuss your specific requirements. And the point is that your MikroTik-based wireless network will perform better with a high-quality antenna. So bear that in mind when you choose your antenna vendor. My contact details are here, so either you can discuss with me later on, or you can contact me via email, phone, whatever. I thank you very much for your kind attention.
Thank you. Do we have questions? Okay. Thank you. Please note that we have changed the agenda a little bit. The presentations have moved up, and when we planned that the raffle will be around the around the 4:30, so a little bit earlier than planned before. So, and the next presentation will be Securing and Testing with MikroTik by Jose Manuel Roman from Spain.